Swayam Prabha. Digital India. Educated India.
You remember when we talked about the basic principles of statistical estimation, there are two competing ways. One is the Fisher's, another is the Bayesian. In the Fisher's, the basic understanding is I am assuming x is constant. In Bayesian, I am assuming x is a random variable with known prior distribution. Then the conditional distribution comes in both the cases. The maximum likelihood estimate, I only use one information conditional density. In the Bayesian, I am going to combine the conditional density with the prior to get the posterior. So, under the Fisher's framework, we already saw x is an unknown constant. We proved the statistical least squares. We proved the Gauss-Markov theorem. We also said that when x is an unknown constant, I can also estimate x using maximal likelihood method, Fisher's approach. So, I am going to fill that gap in talking about a quick introduction to what is maximum likelihood and how do I perform that maximum likelihood estimation. So, this is the case of a linear observation, this is the case of a nonlinear observation. Again, I am assuming x and v are uncorrelated. V is the noise affecting the observation. There are two types of assumptions one can use about V. So, simple assumption is expected value of V is 0, the covariance of V is equal to R. Another one could be a much more stronger assumption, V is normal with 0 mean R. For least squares, I don't need the distributional information, I only need the expected value and covariance. The expected value is always called the first moment, the covariance is called second moment. So, knowing the first two moments of a random variable, I can perform the method of least squares. Least squares method has been around since the days of Gauss. It is Fisher in around 1930s, he invented this notion of maximum likelihood. So, we have now very strong footing on deterministic least squares as well as statistical least squares. So, I am now going to talk about the competing method called method of maximum likelihood to solve the case when x is an unknown constant. So, fx is an unknown constant, there is an observation that contains information about x. Assuming this, I already did least squares. But the Fisher's need the information about the noise distribution, I am assuming normal. X and V are uncorrelated, this is the linear case, this is the nonlinear case. X is the unknown constant, so given x, so Mother Nature has picked x but she didn't tell us what it is. So, I know there is an x that is affecting the observation. So, given the unknown x, I am considering observations z which are normal, which are random. So, it has a probability density function or a probability distribution function. So, P z of x is called the conditional distribution of z given x, because Mother Nature has already picked x and the z is conditioned on the choice by Mother Nature for the value of x. This P z of x, there are two variables, remember, z and x. If x is given and considering z as a random variable that depends on x, That's called conditional that's called the conditional distribution. But if I consider this as a function of x for a given z, see, there are two variables now, x and z. If you consider this conditioned on x, z is a random variable, that's called conditional distribution. The genius of Fisher is that I could also consider this as a function of x for a given z. So what is the idea here? Mother Nature has chosen x. I'm going to measure observation z. Z contains information about x. So the sample has already been obtained. So given the sample z, there's a probabilistic information about the unknown hidden in the sample. So he considers the same function as a likelihood function when considered as a function of x for a fixed z. Fixed z means what? A given sample, and which is the same as the conditional distribution. So conditional distribution and likelihood function are one and the same, except that which one is considered conditioning, which one is considered to be a variable. So as a function of x, it's called the likelihood function. As a function of z, it's going to be called a probability conditional distribution. This was the genius idea due to Fisher. So Fisher in 1920, given z, so what is given z means? I have observed this. So what is the likelihood value of the unknown that will lead to this observation? So I want to be able to maximize the likelihood I want to be able, this is not minimize, this is maximize, sorry. That means maximize the probability of observing the sample z given the unknown. Sorry, this is maximum. So the Fisher's principle is, given the observation, what is the most likely value of the unknown parameter that will make the conditional density or a conditional distribution to take the maximum value. So maximize the probability of observing the sample z. And this can be easily obtained by maximizing x as a function of L as a function of x given z. Please understand, I have already taken samples. The samples are supposed to contain information about the unknown. I don't know the unknown value, but I do know the dependence of the probability distribution on x. So if I have observed some c, what is the value of x that will maximize the probability of observing z for a given x? So that's the idea of maximum likelihood. So maximum likelihood can be in fact stated in terms of the nonlinear estimation problem. Z is equal to h of x plus v. Here E of v is 0. The cross covariance between x and v, please understand, we have already assumed x and v are uncorrelated. X and v uncorrelated means what? X transpose v, expected value of that is 0. That's what uncorrelated means. And I am going to assume my noise is such that I have assumed until now is R. Now I am simply using sigma. Sigma is the matrix, R is the matrix. So this is a m vector, this is a m vector, this is the m vector. So sigma is a m by m matrix. I am assuming V is also normally distributed with the 0 mean, and the covariance is equal to sigma. The cross covariance between x and v is 0. Therefore, z is equal to h of x plus v with this property now becomes the conditional density is given by the conditional density of Z given X is equal to normal with mean H of X with the variance sigmas. I hope you are all with me. So let's look at that now for a moment. Z is equal to H of X plus V. So E of Z is H of X. X is a constant. So this is equal to H of X plus E of V. E of V is 0. This is equal to H of X. So covariance of Z is equal to E of Z minus E of Z transpose minus E of Z, that is given by the definition. But E of Z is H of X. So Z is equal to H of X plus V. Therefore, this is simply equal to E of V transpose, that is equal to sigma. V is Gaussian, H of X is a constant, so Z is Gaussian. Therefore, Z is Gaussian, which is normal with the mean H of X and covariance matrix sigma. So this essentially comes from this argument. So what is the definition of a maximum likelihood estimate? For a given sample, let X hat be the maximum likelihood estimate. The value of the likelihood function at the maximum likelihood estimate is greater than the value of the likelihood at any other estimate. It's like defining the maximum of a function. How do I define the maximum of a function? F of X star is greater than or equal to F of X for any X. So this is how I define the maximum of a function F of X. That's how I define the maximum of a likelihood function. So if I estimate the likelihood function for any estimate, its value is less than or equal to the value of the likelihood function at the where the likelihood function is maximum. Where the likelihood function maximum is called the maximum likelihood estimate, and this is very similar to the estimate we say least square estimate. So subscript LS tells you the least square estimate, subscript ML tells you the maximum likelihood estimate. These two are different methods of estimation. So this means if A and B are positive, so likelihood is simply a probability, they are non-negative quantities. If A is greater than B, log of A is greater than log of B. We already know that. So I can take the logarithm of that. So that essentially tells you the log of the likelihood at the parameter value corresponding to the maximum is greater than the log of the likelihood at any other point. That means I want this to be a maximum. A necessary condition for the maximum is that I can maximize the likelihood function, or I can maximize the log of the likelihood function. So I'm going to compute the gradient of the log of the likelihood function. You all know d by dx of log x is 1 over x. So this is by applying the chain rule, the gradient of the log of the likelihood function is 1 over log of the likelihood function times the gradient. At the maximum, this gradient must be 0. So this is the necessary condition for maximizing the likelihood function. So the x hat ML is obtained by solving this equation star. Now you can readily see what is that we have done. Just to summarize, I have a conditional distribution. Conditional distribution has observation and the parameter. So considered as a fixed value of the parameter, the function of the observation is the probability density distribution. If I consider it as a function of x for a given observation, it's called likelihood function. So if I am observing something, what is the value of the parameter that will maximize the probability of observing that sample? That simple idea of Fisher, that when translated using the mathematical formulation for maximization leads to the necessary condition, which is given by the last equation in slide 3. So instead of just talking in general, now I am going to give an example to illustrate the method of maximum likelihood estimation. Let Z is equal to H of mu plus V. So mu is the unknown vector. Mu is not directly observable. I can observe only H of mu, but that observation is going to contain errors. That observation is going to contain errors. So here, mu is a real number. Mu is R. H is a vector of all ones. So Z is a vector, which is m by 1. H is a matrix. I'm sorry. H is again a vector, which is a m vector. V is a vector of size m. So Zi is equal to mu plus Vi. So each component Zi is a constant plus the noise. And this happens for I is equal to 1 to m. Now VV transpose, this VV transpose must be equal to, I must say this is I times sigma square. So VV transpose are normally distributed to the mean 0 and the covariance is R is equal to sigma square I. That's the covariance of the noise. The covariance of the noise is sigma square I. So please understand, I'm using R sigma to be the noise covariance matrices. With me? So sometimes I call it R, sometimes I call it sigma. Should not confuse anyone. The junctor will tell you what it is. Therefore, if I consider Z and apply these formulas, I already know the distribution of Z. So H mu is a constant vector. So, but Z is probabilistic because of the noise V. I can compute the mean, I can compute the variance. If I add a constant to a Gaussian vector, the resulting vector is Gaussian. So Z is equal to a normal random variable with the mu, with H mu as the mean, and covariance matrix is equal to sigma square I, which comes again from here. Therefore, log of x given Z, I'm sorry, L of x of given Z, this is the likelihood. This is equal to probability Pz of x, which is equal to normal H mu times Z square I. I hope all of you have a good understanding of multivariate normal distribution. Multivariate normal distribution in n dimension is given by, so if x is a normal random vector, with mean m and the variance r, the probability density function in this particular case, and if x is a n vector, this is going to be equal to square root of 2 pi m by 2, the covariance of the square root of the determinant of let me write this down, the square root of the determinant of that exponential minus x minus m transpose R inverse x minus m. So that is the general distribution for the n-dimensional Gaussian random variable. This is the Gaussian random variable in n dimension. So using this, you readily see 2 pi to the power m by 2. Let me change this m to mu. Sorry, I don't want to confuse. So x is a random variable with the mean mu and variance r, and x is the n-dimensional random variable. 2 to the x is the m-dimensional random variable. This is px is equal to 1 over 2 pi to the power m by 2. The square root of the determinant of that, this is m minus mu transpose times m minus mu. This is the expression for multivariate Gaussian distribution. You should know this. This is the standard one. This is the extension of the case p of x is equal to 1 over square root of 2 pi sigma times exponential minus x minus mu whole square divided by 2 sigma square. This is for the univariate case. This is for the multivariate case. Multivariate. This is the univariate. Normal distribution. So according to this normal distribution, I can rewrite this function to be this. You can really say this. And in this case, R is essentially sigma square I. Therefore, you can easily compute the determinant of R. It is simply the product of the diagonal elements. So that this is the quantity related to the determinant. This is the exponential quantity. So you can readily check for this example, the multivariate Gaussian distribution, which is the likelihood function, is given by this. This likelihood function is a function of, when considered as a function of x is mu, is a likelihood function. When considered as a function of z, it becomes the conditional distribution. So there are two variables. Which one is given, which one I'm going to be considering as a function. That's the idea here. So I need to be able to take the logarithm of this, the natural logarithm of Lx given z. So I'm going to take the natural logarithm of that. I'm going to have to compute the gradient of the natural logarithm of L of x. Please understand, that's quite an arithmetic in here. So take the logarithm. So let me rewrite this once more. So I have Lx of z. From here, I'm going to get logarithm of Lx of z. From here, I'm going to consider the gradient of ln x z, ln x z. This is the pathway. So if I consider the gradient of this, x is mu. The unknown is mu. So the unknown could be also sigma square. So what is it I'm now trying to do? I'm trying to do a simultaneous estimation of mean and the variance. Look at this now. I want to be able to compute or estimate the mean. I also want to estimate the variance. So I'm trying to kill two birds in one stroke. I'm given the sample z. I'm assuming the sample comes from a normal distribution with mean mu and the variance r is equal to sigma square I. I'm assuming both the mean mu and the variance sigma square are not known. I'm going to use the maximal likelihood estimation technique to be able to simultaneously estimate the unknown mean and the unknown variance. So I have to compute the variance as a vector. So this is the first component, this is the second component. If you did some good arithmetic in here to compute the gradient, you can verify the gradient expression is given by this, the gradient expression is given by this. It's a very simple, again, calculus problem. I want all of you to be able to do this. So from here to here is a homework problem I want you to verify. Please understand. If I were to give all these expressions go over the class, it will fill 10 more pages. But these are simple exercises as a graduate student you should be able to do. Even as an undergraduate, senior level student should be able to do these calculations very easily. These are simply exercises in multivariate calculus. It has nothing to do with estimation. So you have to understand when a statistical idea is used, when an optimization idea is used, when the matrix idea is used, when the vector space idea is used. So you can see in this analysis, sometimes it looks like matrix algebra problem. Sometimes it looks like a minimization maximization problem. Sometimes it looks like a statistical problem. So statistical properties, matrix properties, vector space properties, optimization properties all come into a hue, and you should be able to separate. If you can able to separate, then you win the game. So I would like you to be able to verify this. I have to set this to 0. If you set this to 0, you can readily verify z bar which is the sample average, that's the maximum likelihood estimate of the unknown. Wow, that's a very good result. We have seen this result is also a result coming from least squares theory. Average is the best least square estimate. Now I am showing average is also the best maximum likelihood estimate of the unknown mean. Now the variance of the estimate is 1 over m zi minus z bar whole square. Both are unbiased estimate under the maximum likelihood consideration. Now I am going to, so now hope you understand the basic idea of the maximum likelihood estimation technique. Maximum likelihood estimation technique. So these are both estimates of the unknown mean and the unknown variance coming out of the maximum likelihood estimation. I am doing this simultaneously the two unknowns. Now there is a theorem due to Rao and Kramer. Kramer is a famous probabilist statistician. Rao and Kramer have proved independently a theorem. This relates to the variance of the log likelihood estimation. So let Ln L of x be the log likelihood estimation function. This be the Hessian of the log likelihood function. Please understand, this is the log likelihood function. So I'll talk about the three levels. Likelihood function I want to talk about Pz of x, which is equal to Lx of z, then Ln of Lx of z, then I'm going to be talking about the gradient of this with respect to that. I'm going to be talking about the Hessian of this with respect to that. So the gradient of the log likelihood, the Hessian of the log likelihood. We already know Hessian, gradient, Hessian, how to compute them. It can be shown the inverse of the estimate of the variance is called the information matrix, that is given by the negative of the expected value of the Hessian is also equal to, now please look at that, this is the gradient, this is the transpose of that, the outer product. Sometimes this is called the score function. So this is also equal to the expected value of the outer product, expected value of the outer product. So Ix is called the information matrix. Information matrix, as I already know, is the inverse of the covariance matrix. So the covariance matrix is the inverse of the inverse of the information matrix. So this is the information matrix. This is the inverse of the information matrix, which is the estimate of the covariance. So what does the Kramer-Rao bound say? If this is the estimate of x coming from, the maximum likelihood, then for any estimate x hat, the covariance of the estimate given x, because x is the unknown constant, is greater than or equal to the invariance of the with the inverse of the invariance, inverse of the information matrix. Inverse of the information matrix, and the information matrix depends on only the likelihood function. So this is an universal bound, and this bound is called the Kramer-Rao bound. So if the covariance of any estimate is greater than the inverse based on the log likelihood function, if it is equal, it is optimal. Please understand, if a quantity if a quantity x is always greater than or equal to a, when x is equal to a, we say is the boundary value, is the best value. Therefore, the covariance matrix is always greater than the inverse of the information matrix, and the information matrix is given in terms of the likelihood function. And there are two equivalent expressions for the information matrix. I'm not going to derive these information matrices to say they are equal. They are given in the book by Kramer, and they are beautiful results. So what does this say? This is called Kramer-Rao bound. So when you are estimating the variance, I want to be able to find out, can I make the covariance be as small as possible, the variance as small as possible? What did Kramer-Rao say? When I am trying to estimate it, the covariance matrix is lower bounded by another matrix. The another matrix is called the inverse of the information matrix. So this is the universal bound, that's called Kramer-Rao bound. So in the nonlinear case, you can find this information matrix by this expression, by this expression, by this expression, and we can use this expression to be able to derive the lower bound on the estimates of the covariance. Again, this is a beautiful result that comes from the book by Meltzer and Cohen, Decision and Estimation Theory. So in summary, what is that we have done? I have just given you a taste of the whole world of maximal likelihood estimation. Here, Fisher's idea, the unknown is fixed, non-random. Given the unknown fixed by Mother Nature, I can sample. The distribution is coming from a conditional distribution Pz given x. I can consider this as a likelihood function by considering as a function of x instead of z. If I can consider the likelihood function, I can consider the log likelihood function. I want to be able to maximize the likelihood function. Maximizing the likelihood function is the same as maximizing the log of the likelihood function. So by maximizing the log of the likelihood function, I can estimate parameters. I illustrated the estimation problem by estimating simultaneously the mean and the variance parameter sigma square. That involves techniques from multivariate calculus computing the gradient Hessian. So we derived expressions for the maximal likelihood estimates. Then in the end, we mentioned about the Kramer-Rao bound. Kramer-Rao bound essentially tells you the variance of the estimate is lower bounded by an information, by the inverse of an information matrix. The information matrix itself is related to the Hessian or the outer product of the gradient with itself. So this is simply a sampling of the results from statistical estimation theory. I would like you to look at the books by Meltzer and Cohen for much more detailed descriptions of maximal likelihood technique. Thank you. With that, we conclude this part of the chapter.